All right, I guess we should make a start. Good morning, good evening, good afternoon, everybody. Or as I'm coming from Australia, so I'll use good day for everyone. That will cover everything. Thank you all for coming to this seminar organized by the Transport Science and Logistics Society of Informs. So today we're honored to have Dr. Liu Yang to present on a topic in terms of quite relevant in our current sharing economy. So her topic will be two-sided reinforced learning for dynamic mobility on demand management with mixed autonomy. We will have the presentation soon to start, but before we start, I just want to make a quick introduction to Dr. Liu. So Dr. Liu currently is an assistant professor in the Department of Civil and Environmental Engineering and the Department of Industrial Systems Engineering and Management at National University of Singapore. She received her bachelor from Tsinghua University, Master of Philosophy from Hong Kong University of Science and Technology, and PhD from Northwestern University. So I think without further ado, I'll pass the floor to Dr. Liu. And thank you for agreeing to have this seminar for us. Thank you very much.
Okay, thank you, Professor Wu, for your introduction and invitation. So let me go full screen first. Okay, can you see my screen?
Yes, yes,
okay,
I can.
Thank you. Hello, everyone. I'm Yang Liu from National University of Singapore. So today I'm glad to have the opportunity to share some of our work in sharing economy. So I want to acknowledge the co-authors of this work, Ms. Jiaohong Xie, who is also attending the seminar today. So she will also participate in the Q&A session. And also my colleagues, Professor Chen Nan from National University of Singapore. Okay, so today I would like to present the two-sided deep reinforcement learning framework for dynamically determining the operation decision for mobility on demand with mixed autonomy. Okay, so this is the outline of my presentation. So first, so we have witnessed significant growth in the past decade, where we see the growth in the mobility on demand system. So we can share the vehicle space so that we can better utilize the limited transportation resource so that we can reduce car ownership and relieve traffic congestion, greenhouse emission, and also reduce the need for parking space. So finally, we can enhance the traffic network efficiency. So we have seen the growth of the ride-hailing companies such as Uber, Grab, and Didi. And also in the past few decades, we have also witnessed the significant growth of the AV technology. So autonomous vehicle has been implemented and on trial for many cities. Okay, and also there are many advantages of AV, such as we can reduce the need for manpower, and we can provide stable and reliable service, and also we can enhance the road safety. Okay, so on the left lower corner, we have this autonomous shuttle that has been running in NUS campus. So this is actually one of the first trial in the mixed fleet conditions. So the AAV actually operate with other human-driven vehicle, buses, and also motorcycles. So it's giving the benefit of AV. So the MOD platform has many MOD platform have announced to introduce autonomous vehicle to their fleet in the near futures. So it is predicted that the AV market penetration will gradually increase until it will be fully replaced. It will fully replace the human-driven vehicle. So we can see it will take a very long transitional time, maybe 40, 50 years until all the vehicle will be replaced with AVs. Okay, therefore, the AV and the conventional vehicle will coexist in long run. So most of the MOD platform will probably adopt a hybrid model where they need to consider both operation of AV and CV. So this motivate our study. So we want to address those challenges of managing the mixed fleet, and the real-time decision must be made quickly and efficiently, while the uncertainty in the travel demand must be fully considered. And also how to address the asymmetric demand, which lead to the imbalance issue between the supply and the demand in the mobility system is still exist. Okay, and also while when we take advantage of the AV technology, we also need to consider the different characteristic of CV and AVs, and how to think of way how to model and capture the complex interaction among human driver, AVs, and operator. And lastly, it is predicted that because of AV technology, it may eliminate millions of driving jobs. So we want to address the equity issue and ensure a smooth transition. So when we take advantage of the AV technology, we don't want to harm the interests of drivers, so that the system can have a sustainable solution for long run. Okay, so this is our motivation. And by looking at the literature in the past, so one of the major challenges is to address the imbalance between the demand and the supply. And there are two typical solutions for this issue. So first of all, we can make use of the pricing scheme to dynamically influence the demand side, okay, such as using surge pricing or incentive policies. In the second solution, we can use the vehicle relocation. So to optimize the vehicle relocation and matching decision to better match the supply with demand. Okay? And also there are studies which investigate the mixed fleet, but mainly focus on long-run equilibrium. So the dynamic problem of mixed fleet is not well studied. And reinforcement learning has been applied and extensively studied in the transportation field to examine the traffic signal control problem, and also the adaptive routing and fleet management. And so for managing a large-scale a mobility on-demand system, so because of the state space is huge, and we use approximate dynamic programming and reinforcement learning to address this issue. We call the curse of dimension. And reinforcement learning can be categorized into two areas. So in the single agent reinforcement learning, so the centralized decision maker, which is usually the operator or the platform, which optimize the vehicle operational decisions. And in the decentralized multi-agent reinforcement learning area, so we consider the behavior of drivers. So each driver will try to optimize their own decision according to their compensation and the cost. So in this study, we actually use multi-agent reinforcement learning to consider the decision of both operator and the drivers. So this is the research gap we have found from the literature review. So first of all, to our best knowledge, so there's no study which use deep reinforcement learning to study the dynamic decision making for mixed fleet management. Okay, so there are studies that focus on pure autonomous vehicle or pure conventional vehicle management. And also, most of the study in the past focus on the demand side. So how to use a pricing scheme to adjust the demand, to influence the demand, so that the demand and supply can be better matched. So here, alternatively, we try to use dynamic commissional fee to influence the supply side. Okay, and those challenges still exist. How to address the imbalance between demand and supply dynamically. So as shown on the plot here, where we use the real-world data from New York City by looking at the heat map of taxi trip requests in April 2014, we can see the demand is asymmetric during the evening peak hour. So we have the hotspot in the city around the Central Park area and also the two airport. Okay, and also how to address the asymmetric and stochastic demand across time and space is another challenge. And lastly, we want to also consider the behavior of drivers. So driver actually play a non-cooperative game. So they try to make their own decision to make their own benefit. So the distinct characteristic of AV and CV must be considered simultaneously. Okay, so this is the framework we propose to for the future mobility on-demand system. So it's not happening now, but we believe this will be something useful for the future mobility system. So we consider the framework which we can study the real-time operational decision for the mixed fleet, and this actually provide a practical protocol to address operational decision of MOD platform with heterogeneous sources. And we explicitly consider the stochastic nature of the travel demand and the distinct behavior of the two type of fleet. And we hope this will be a sustainable solution for the MOD system with a mixed fleet, and we can use this to facilitate a smooth transition toward a fully autonomous system. Okay, and then we will talk about the numerical study based on the trip data from New York City. Okay, so here is the problem statement. Okay, so we consider a realistic case, okay, where we have this mixed fleet MOD platform, and the human driver may choose to relocate themselves freely, and they will be able to learn the strategy to maximize their own compensation. So this is the same phenomenon we have observed for the taxi driver. So taxi driver will learn their own optimal strategy. And in contrast, AV are fully compliant to with operations with the platform's decision. So they will follow the decision order from the platform. So to achieve a high level of service, we propose the platform to prioritize the human drivers in the matching decision, so that we will protect the benefit of human driver. But at the same time, we will use a dynamic commissional fee to influence the driver's behavior, so that we can achieve a high level service, and we can also make the driver benefit and also we can complement the service by using AV service. Okay. So first of all, from the perspective of operator, so the operator actually act as a supervisor agent, okay, who make decision as a centralized manner, giving the real-time information about the state. The platform matches order to drivers and determine the optimal relocation decision for AV, and also what is optimal commissional fee that should be charged to the driver. So we use a piecewise linear function. Okay, so the piecewise linear function here is used to adjust the commission fee according to the ratio. So let me try here. According to the ratio between the demand and the supply. So we look at the ratio of the number of requests and the number of vehicles available at a specific location and the time step. And the idea here is we try to use this function to maintain the demand and supply ratio equal to 1, close to 1, so that we can reduce the gap between the supply and the demand. So we reduce the imbalance between the demand and supply. Okay, and for the operator, whenever an order is fulfilled, one reward is collected, and the objective is to maximize the cumulative reward. And for the driver agent, so we consider driver agent are non-cooperative. So they will make their decision in a decentralized manner. And so they can make the observation of the state, but they don't have the full information of the system state. So by looking at the current location and time, they will make the action so that they will choose where we want to go after they complete one order, and whether they can stay in the current location, wait for the next customer. And then the reward for the driver agent will be the profit for taking an order minus the commission fee and the relocation cost. Okay, so every driver try to optimize their own profit. And then in order to consider both the driver and operator's decision, we propose this two-sided multi-agent reinforcement learning approach. Okay, so in this framework, so we have the operator on one side, which act as a supervised agent, and then we have the driver's agent on the other side, who make their own decision in a non-cooperative way. And then so the decision procedure is simulated and interacted in the same environment. Okay, and then the operator will make the decision, such as the relocation of the AV and the optimal commission fee, and then the driver will make the decision where they want to go after they complete one order. Okay, and in order to solve the problem, so we use the actor critic method. So here actually each agent will have two network, a policy network and a value network. Okay, and so we have the value network. So here the value network or the critique will evaluate the value of the current policy by observing the environment feedback. And then the policy network, which is the actor, will be responsible for decide what is the action to take based on the observation. So for each for actor and critique, each of them will have a deep neural network which combines the reinforcement learning and deep neural network so that we can make the decision using the A2C algorithm. Okay, so here for the actors, so they will try to make the decision so that by minimizing the loss function of the critique will make the decision to minimize the loss function, while for the actors, the objective is to maximize the gradients of the actors. Okay, by combining the value-based and the policy-based method, so the A2C method can reduce the variance with respect by comparing to those pure policy search method. Okay, so considering for the operator, so we have the centralized decision for the operator. So the operator will make the two type of decision. So the operator need to make the decision of relocation and also the commission rate. So in order to do that, we modify the policy network and propose a two-headed network. Okay, And the operator will have two types of actions. So we have the relocation head to produce a relocation decision, and then we have the commission rate head to produce the optimal commission fee. And we have this will allow us to keep the common information in the hidden layer, so that we don't need to train two neural network for the two type of decision, which can greatly reduce the computation effort. And then in order to strike the balance between the exploration and exploitation, so we use entropy loss. So we actually try to minimize the gradient minus entropy loss here. So for the drivers, since we have in the real world network, we may end up with thousands of drivers. So it will be computational intractable to maintain a neural network for each agent. So therefore, here we do not model each individual's decision using the neural network. So we assume that all the drivers are homogeneous, so that they share the same states, state space, action space, and reward function, so that we'll be able to train the decision of agent using one neural network. Okay, and then the mean field method assume each agent is only affected by the mean effect of its neighbor. So here the agent will only interact with the agent in the neighbors. And then we denote the Q function here. So we use the Q function as a pairwise local interaction to approximate the interactions between one driver agent and all the agents that in the neighborhood. Okay, and then this is the algorithm. So in basically this algorithm has two loops. So we have the outer loop, where we count the number of episodes, and the inner loop, which which iterates the time from 0 until the end. And then each episode will have two stages. So in the first stage, the agent will explore the environment and collect the experience. And then in the second stage, so we will randomly sample a batch of experience to update the four neural network. And then the numerical study has been conducted using a New York City data set. So we use a taxi data set from New York City, which give us a realistic setting for the mobility on-demand system. And the map is discretized into grid, and we look at the evening peak hour from 4 p.m. to 8 p.m. And then the time window is discretized into a 10-minute interval. So so the fleet size is 6,000 and the demand volume is 90,000 in the basic scenario. And then later we'll adjust the fleet size and demand volume to do the sensitivity analysis. And then for the policy network for the driver, we use a 3 hidden layer network with a size here. And then the other network are has four hidden layers with node size specified here. Okay, and the ReLU activation function is used, and learning rate and discount factor is listed here. And for the simulation environment, so we simulate the behavior of driver and the environment using the simulator. So I will not go into details. In general, we simulate the process of a random demand request arrive, how the platform makes the decision, and then how the driver and AV is relocated to the other desired locations. Okay? And then we make the observation of the environment and to calculate the reward. So this is the data sample from the trip data where we are giving the pickup time and drop-off time of each trip and the number of passengers on the taxi, and then the pickup longitude, latitude, and drop-off longitude and latitude, and the fare of the trip. As we can see, there is a distinguished pattern for each day of a week. For example, if we look at the Saturday and Sunday, the demand pattern is significantly different from what we observed for Monday to Friday. And to benchmark, to showcase the performance of our policy, so we actually benchmark with a simulation policy. Okay, so in the simulation policy, we just simply distribute the vehicle to the neighbor grid randomly with a probability 24 proportion to, with a probability proportion to the demand volume of the neighborhood grid. And then we also benchmark with the MA policy, so where we still make the optimal AV dispatching decision without charging the dynamic commission fee. And then this is our policy where both AV's relocation decision and also the commission fee is optimized. Okay, so by looking at the training curve here, what we can see is our policy outperformed the MA policy in terms of the order fulfillment rate. So order fulfillment rate represents the percentage of order that has been fulfilled. It is an important indicator for the level service. And then also in terms of the total revenue, so the second plot gives us the total revenue. We can see our policy also outperform MA policy. And we also adjust the CA ratio. So CA ratio is a ratio of the number of conventional vehicle to the number of autonomous vehicle. So with higher CA ratio, so which is a green plot here, which means we have a high market penetration of conventional vehicle and low market penetration of autonomous vehicle. What we can see here is with high CA ratio, which is a blue curve here. So with higher market share of the autonomous vehicle, we can actually further improve the level service. So which makes sense since AV will fully comply with the platform's decision, and it will optimize the remaining order in a centralized manner. Okay, and then we also benchmark the three policy. So this is a table which lists the full information of the benchmark results. So the implication here is what we observe is a significant improvement in the gross merchandise value, which is a total revenue, compared to the MA policy and simulation policy. And also, we also observe the improvement in the order fulfillment rate compared with the MA policy and simulation policy. Okay, and with higher AV penetration, it actually yield better performance. Okay. And then we further look into the gap between the demand and the supply throughout the city. So by looking at the geographic information of the gap, okay. So by looking at the high CV AV ratio and the low, so this is high, and this is a low CA VAV ratio. So what we can observe is the demand and supply gap is narrowed while commissional fee is dynamically determined. So if we compare the gap between demand and supply for the two in both plot, we see the gap has been reduced. So which is the orange bar here. And then the worst case is a scenario where we have a low AV penetration and without the dynamic commission fee. So the commission fee scheme, so the dynamic commission fee scheme and the centralized AV reposition actually alleviate the unbalanced demand and supply by sending those vehicles to location with higher demand. Okay? And then by looking at the different level of demand, so we actually conduct some sensitivity analysis on the demand level. So we just do this naive way to factor the demand using a factor, which is the x here. And then what we can observe is the MA and CF policy, which is our policy, show the largest advantage in the two performance metrics compared to our benchmark case, especially for those cases when the demand is high. Okay, and our policy guarantees satisfactory order fulfillment rate, except those are extreme demand rate. Okay, so when the demand is high, our policy can also still can still fulfill about 60 and 70% of the order. And then lastly, we look at the profit and the cost. Okay, so this plot illustrates the cost and the profit. So we can see the proportion of driver's profit and the proportion of the AV's profit. Okay, so what we can see here, the cost and the commission fee can be ignored, which is quite small compared to the total profit. So we suspect this is because of the parameter setting of our cost function. So we are still working on more numerical experiments. And so when we change the demand level from 0.67 to 1.67, so the total profit of the AV in the 3 policy will increase rapidly because of the gap between the number of driver and the number of requests. And then our policy still can still make both drivers and operator better off. So this is one of the objective of our study. So we do not only want to optimize the system performance by optimize the operator's objective. At the same time, we still want to provide sustainable compensation scheme to the drivers so that they will be able to retain a large number of driver in the platform in long run. Okay, so to conclude, okay, so we investigate the dynamic operation problem of a MOD system with a mixed fleet of both AV and CV, and we propose a two-sided multi-agent deep reinforcement learning framework where the operator makes the centralized decision and the driver makes the decentralized decision. Okay, so we consider the behavior of driver, and also we try to protect the benefit of driver while we make the matching and relocation decisions. Okay, so this framework can be potentially applied to other type of operational problem in MOD, such as we have heterogeneous sources, such as we have dedicated driver and part-time driver. Okay, and so the dedicated driver may fully comply to the decision of operator, while the part-time driver makes their own decisions. And this is the realistic environment. We use the real world data from New York City, and the policy can make the decision in the online manner, so we can make quick decision, and which can tackle the system uncertainty. And then we show that the result outperform the benchmark case in different metrics, and in terms of the profit of the platform and also the level of service, which is fulfillment rate. Okay, and then the decision has to be made in advance to eliminate the imbalance between the supply and the demand. So for the future direction, we we are thinking the study can be extended to consider heterogeneous drivers. So here we assume drivers are homogeneous. Maybe a driver may have different strategies and different preferences. And then we can consider the electric AV, where electric vehicle has the problem of the charging and battery range. And then we need to consider all the constraint and the charging decisions into the framework. And also this system will be more efficient if we can incorporate the one-to-many matching problem, so that one vehicle can go pick up multiple drivers in the same direction, so that we can further save the space of the private vehicle. Okay. So this is the end of my presentation. So I'll be happy to address your questions. And also, as I mentioned, Jiao Hong, who is the first author of this paper, is also attending this seminar. So she can also participate in the Q&A session.
All right, great. Thank you very much, Dr. Liu, for your interesting presentation. Now I'll open the floor for questions and answers. And I think I have one hand raised. Layla, do you want to start your questions?
So first of all, thank you very much for the nice presentation. I really enjoyed it.
Thank you.
One thing where I was not entirely sure if I understood it correctly was, does every agent learn independently, or do you still have one function where you optimize for all agents jointly?
So actually, each agent actually learn independently, but they share the same environment.
Ah, okay. So it's even possible that they potentially eventually learn different things depending on their experience.
That's a good point. Yes. So I think the learning of, especially the learning of the driver, is homogeneous at this point. But I think this is a good point. So also, as I mentioned, in the future directions, because the paper we submitted and the referee also raised up this question, whether we can consider different type of learning, different type of strategy for the drivers.
Yeah, we just assume if someone always drives in Lower Manhattan, this person might learn something else than someone who always drives in Upper Manhattan. And this might not even be a different strategy. It might just be random at the end.
Yes.
Yeah, so thanks.
Thank you. Any other questions? Jiao Hong, you want to add more about the question?
Okay. So about this question, I would like to say that because the multi-agent setting, the number of drivers is very large, so it's impossible to generate different type of agent settings according to each individual drivers. So we assume they have the same structure of the learning architecture, and they share the same parameters in their reinforcement learning networks. So actually, this setting means the experience of each drivers will give some improvement on other drivers' learning strategy. So I think for heterogeneous driver behavior, it can be an interesting future direction.
Yes.
I just want to comment on that. Maybe like a compromised approach would be you have like a set of kind of strategies, for different types of drivers. You can like decide. Some drivers will basically drop off a passenger, and then will decide wait in the nearby. And other passengers they know, okay, I know there's a good place to have a higher chance to be called, something like that.
Yes, yes, yes. We also discussed this before. So we have the active drivers who actively searching for customers, and then we have these passive drivers who are lazy, just stay in the same area, just wait for the next order to arrive.
Mm.
If you optimize them independent, if they all learn independently, it might also affect the velocity or the time until you actually reach a stable state. Because of course, if you have 10,000 people who all learn their own thing, then of course the experience that they can gather is a lot less, even if they are homogeneous. They always just every day they generate a little bit of experience, but if they actually share it and you have 10,000 people or 15,000, I think that's the number of taxi drivers in New York, if they can all share it, then of course you learn a lot faster.
Yes, yes.
Might be
Yeah.
super interesting actually for a taxi company to for the AV company to exploit that the taxi drivers or that the conventional vehicles take forever to actually adapt that.
Yes,
True.
so for actually the taxi company, so they had this problem to how to direct the taxi driver to the right location. Since taxi driver they are uh, have the good knowledge of the road network traffic conditions, so they know there's a hotspot in the maybe in the CBD area, but they just don't want to go because they will not get sufficient compensation by going to those hotspots because it's too congested. So that's why we consider the dynamic commission fee could be one way we can actively encourage and influence the taxi driver to go to different locations. Okay, I think there's one question in the chat box.
Yes. Yeah.
Do you
So
consider the real street network to move to the neighborhood grid? Okay, good question. I think we didn't since but the travel time was actually sampled from the real network. So Zhaohong, you want to maybe talk about the details? Can
Actually,
you see
we
the
only
question?
yes,
Yeah.
yes. Actually, we only consider discretize the service area into hexagonal grids. So we do not explicit consider the real street network and the connectivity between each grid, because I think it's a common practice in ride sharing companies like DD or other sharing companies. So they use hexagonal separation of the service area to for the convenience of computation, and because the you can have the same distance from one hex to its neighbors.
Yeah, but the only information we need is the travel time, right? So
Oh, yes.
yeah, so
So
I think if we want to consider maybe a congestion effect, then we need to go and use the real network, real road network. But for this, for our study, we only need the travel time information. So the travel time information was actually collected from the trip information, right? Since we have the drop off and pickup time in the maybe in the past in the historical data. So how we estimate the travel time is to sample from the real trip data.
yes.
But for in the case that we when we consider the impact of AV, so for example, I have a large fleet size with many AVs, then we might need to consider the impact of the relocation decision on the traffic congestion. Then I think the road network will be needed for predict the traffic congestion effect. Another question? Oh, no question.
Okay, we have yeah, Amr. Yeah, please speak.
Hi, maybe it's related to the commission comment that you make, but can you incorporate some policy measures into the model, like for example, to accelerate the learning process, like fees on cruising empty or stuff like this?
Sorry, I'm not sure I get your question. You're talking about the commission fee, right?
No, so I'm saying, yeah, the commission, maybe it's related to the commission fee, but maybe there are policy measures that can take by local government, like if they don't want just empty vehicle to cruise the streets.
Right.
So they can put some fees. So maybe that can accelerate the learning process or do something like this.
So you are suggesting, yeah, go ahead.
Are you suggesting to use to propose some policies and regulations from the government?
Yes, if that can be incorporated into the model and to accelerate the learning process, perhaps.
Okay. But I don't get the connection between the policy and the learning process. And I think our commission fee scheme is actually
yeah, it pretty resembles this. So it probably will be like the same, in the same manner. It will be incorporated into the model.
So I think the question is suggesting we can consider how the commission fee can be used as an instrument to prevent too many vehicles without passenger running on the road. For example, AV, it is expected that maybe AV relocation may increase the traffic congestion in long run. So maybe the commission fee can be also considered to reduce those so we call the downtime in taxi industry, to reduce the inefficiency of the road network.
Yes, exactly.
Yes, I think that may be potentially considered for our framework, so that so currently the commission fee is set as a piecewise linear function. Actually, our objective, the reason we use this commission fee, this function, is we try to get our the number of demand, the ratio of the number of demand over the number of supply close to 1. Okay, so actually somehow we have already considered that, since if we can have the number of requests that is roughly equal to the number of vehicles nearby, then we can prevent, or we can reduce the relocation, or we can further reduce the relocation cost. But I think we can also further look into the relocation cost. Maybe we can also put a higher penalty for the relocation cost, and maybe the commission rate will be adjusted in the way that the relocation should be minimized.
Yeah, that's pretty much what I meant. Yes, thank you.
Yeah, thank you. Thanks for your comments. Any other questions?
Yeah,
yes.
Any other questions? Dr. Liu, actually, I just want to like get a little bit insights from your experience from this study here. apparently we see the reinforced learning approach outperforms the benchmark policies.
Yes.
So, based on your observation from the numerical experiments, what do you think are the main contributing factors in this process?
You are asking the contribution of this framework, or
Like how this reinforced learning approach helps, we get a better performance?
okay. So I would see first we want to study a realistic environment so that we consider both the behavior of driver, and then we optimize the objective of operators. So because we cannot assume all the drivers will follow the decision or follow the order of the operators. Okay, so I think this is one thing. Since if we compare to the system with a pure AV, which means we cannot outperformance them, since AV will be fully compliant with the decision of operators. Okay, but still we try to try to influence the driver's behavior using this dynamic commission fee. Okay, so that the driver's decision can be influenced, so they can learn and they can be influenced in the long run. And so this reinforcement learning approach, I will see. So we have we have considered in the case that we are giving the real time data, so that we receive the real-time data from the platform, and then we can help the operators make the real-time decision. I think this is the advantage of the reinforcement learning. And but in order to capture the decision of operator and driver simultaneously, so we need to use this two-sided framework to incorporate their decision into one environment. I think this is probably one of the advantage of this method. I think for single agent reinforcement learning or conventional optimization approach may not be able to address this complex environment in a real-time manner. So I think this is probably the advantage of reinforcement learning. Xiaohong, please feel free to add.
Yes, and regarding to the performance of the our reinforcement learning framework compared to the two benchmarks, it outperforms the first simulation benchmark. It is straightforward to explain because it optimizes the decisions of both drivers and operators. So the simulation benchmark just allocates the AVs and drivers to their neighbor grids according to a heuristic rule. And for another benchmark, MA policy without the commission fee, our policy with commission fee can outperform it because it considers the commission fee and regulates and incentive drivers to avoid them gathering at certain hotspots. So it improves the system efficiency and level of service.
Okay.
Yes,
Yeah.
that's my answer.
Right. Thank you. Do we have any other questions? Okay, going once, twice, gone. All right, so I'll probably will give a few minutes back to your time. I know everyone is very busy. Okay, thank you very much again for Dr. Liu and Joe Hong for joining this seminar, for your presentation here. It's greatly appreciated, and thank you all for attending this seminar at different times across the world. Thank you very much.